Hey guys, before we get into final exams, there are a few more derivatives that we need to talk about. We need to talk about derivatives of logs and natural log problems. We need to talk about derivatives of exponential problems. We need to talk about inverse derivatives, some other trig derivatives. Um, and then we're going to learn what's called L'Hopital's rule here in a little bit. But let's go ahead and talk today. We're going to do section 5.1, which is natural log derivatives. Okay, natural log is an ln function. And let's first talk about the natural log graph and what it looks like and what certain values are. Because natural logs will come up every so often on your test. And it's important that you know what certain values are, because if this were a non-calculator question, would you be able to tell me what the natural log of 1 is, or what the natural log of 0 is, or what the natural log of 2 is, and then what happens if we get bigger than 2, stuff like that, okay? Because it does come up enough times that you need to know what the natural log values are without using your calculator, okay? So you could, I guess, plug this into your calculator for now, but then after today, if I ask you for certain values like natural log of 0, you need to memorize what that equals. If I ask you natural log of 1, what does that equal? Or maybe even natural log of 2, what does that equal? And then kind of have a general idea what happens before 1 and what happens as we go higher into values bigger than 2. Okay? If you plug it into your calculator and you plug in natural log of 0, what happens? You end up getting an error, don't you? That means that the derivative doesn't exist. What's happening on your graph is you get a graph of a natural log that kind of looks like this. A natural log graph kind of looks like that. Okay? There we go. That's much better. All right. Because at the natural log of 0, when x equals 0, there is no value there. There's actually an asymptote, a vertical asymptote there. So when I ask you for natural log of 0, you need to know that the natural log of 0 does not exist. Okay? But there are values just greater than 0. If you plug in natural log of 1, what do you get? You should end up getting 0, right? So the natural log when x equals 1 is 0. It touches the x-axis at x equals 1. Okay, so that's an important value to know when we're doing derivatives and sign charts and testing values. What is the natural log of 2? You put it in your calculator and end up getting 0.69 something, right? So as we're going through, what happens as we go higher into values? Natural log of 3, natural log of 4, natural log of 5. Those values should increase, right? They might increase slightly, but they still kind of increase. If you look at the graph kind of looks like that. You have a vertical asymptote at 0. There are no negative natural logs, so it doesn't go past 0. Natural log of 1 is 0. Natural log of 2 is 0.69. Natural log of 3 gets a little bit higher than that, and so on. Okay? So keep that in mind as we're doing derivatives of natural logs and testing values, okay? All right, let's learn a few rules and a few derivatives. Let's first talk about log properties. These properties work with natural logs and regular logs, okay? Again, what is the natural log of 1? 0, make sure you know it. If I have a natural log problem where I am multiplying two things, instead of doing the natural log of their product, the two things multiplied together, what I can do instead is I can break these up into smaller pieces. And I can do the natural log of A plus the natural log of B. Sometimes this helps when we're finding derivatives, so we don't have to use some weird product rule type of thing. We can break them up in what's called expand them into little pieces, and then find the derivative of each little piece. Okay, it's a little bit easier when you're doing derivatives sometimes to expand it into little pieces instead of trying to do the whole big thing. So anytime I'm multiplying, what I can really do is I can expand it into an addition problem. Okay? I don't know if you remember this from algebra. If you have a natural log and you have an exponent here, this exponent can actually come out to the front of your natural log and turn it into n times the natural log of a. So anytime I have a log or a natural log with an exponent, I can actually take that exponent forward and put it in the front. Okay? When I take a natural log problem and divide it, instead of dividing one natural log problem, what I can do is I can expand it into a bunch of little log problems, where I do the natural log of A minus the natural log of B. So a multiplication problem expands to addition, and a division problem expands into a subtraction problem, okay? This is going to help us when we start doing some derivatives. Let's go ahead and practice a few problems before we start going into derivatives. And all I want you to do on these two problems is expand it. I want you to break this up into little pieces if you can. So what do you think we're going to do here on the first one? The first thing I see is that radical, right? And what do we normally do with radicals first before we start doing derivatives and anything like that? Can we take it and make it, instead of a radical, can I make it a 1/2 exponent? Then I notice that I have an exponent and a log problem. So then can I take that exponent and bring it forward, changing it to a 1/2 natural log of 3x plus 1. Okay? We haven't done anything yet with addition problems with logs, so that's about as much as I can expand it. I'm going to go ahead and leave it 1/2 times the natural log of 3x plus 2. Okay? What about b? Lots going on here. I see some exponents. This is a cube root. I know it kind of looks weird. It looks really close to that other x, but it's not an x cubed. It's the cube root of all that stuff. We got a lot going on here. Let's do it piece at a time. Okay? Let's go ahead and take this top piece, and I'm going to do natural log of x squared plus 3 squared. And instead of dividing, when I expand it, can I expand it into a subtraction problem? Right? And then I'm dividing a whole bunch of stuff, so I'm going to put a big old bracket here and put all the stuff that I'm dividing by. I have a natural log of x, right? This little x right here. And then I have this other thing that I'm technically multiplying the x by. So when I multiply, what does it expand into? It expands into a plus an addition problem, right? It expands into an x squared plus 1, and instead of saying the square root, oops, I forgot my natural log here. Can I put a 1/2 exponent? But can I go a little bit farther with these? Can I take this exponent here and bring it down, making it a 2 natural log of x squared plus 3? And then can I take this other exponent here, this 1/2, and bring it forward, making that a, oh wait, it wasn't a 1/2, isn't it the cube root I said? I said that earlier, and then I made a square root. All right, let's make it a 1/3 with a natural log of x squared plus 1. Okay. You could distribute this negative through if you wanted to. It would mean the same thing. To me, it's a little bit easier to tell that I'm dividing by that whole entire chunk if I keep it in parentheses. It looks like that's as much as you can expand it. So I'm going to go ahead and leave it like that. Okay? All right, so now we practice expanding. Let's go ahead and learn some derivative rules, and then we'll put it all together and find derivatives of these natural log problems. Okay? So the rules for deriving natural log problems. If I have the natural log of x and I want to find the derivative of the natural log of x, my derivative of natural log of x is 1 over x. Okay? What I'm really doing is I'm taking the derivative of x, which is 1 over x. Derivative of the inside over the inside. Okay? So using that, look at this natural log of u. I'm going to take the derivative of the inside over the inside. So the derivative of natural log of u is u prime over u. Okay? What that means is if I have more inside than just an x, let's say maybe an x squared on the inside, I can take the derivative of my inside, which is 2x, over my inside, which is x squared. I can reduce that a little bit, but that would be my final answer. That's the derivative of a natural log of x squared. Okay? All right, so anytime I have a natural log, I can take the derivative by, again, doing the derivative of the inside over the inside. The last derivative rule that we're going to learn is if I have a natural, not a natural log, but a regular log problem with a base on it. Okay? It doesn't show up too often, but it is something that you should know. Why not? You know, if it does show up, you should know it, so that way you can get a free easy point on the AP test. To find the derivative of something that looks like this, you're going to take, again, the derivative of the inside. Then you're going to take the natural log of that base, natural log of a, over the inside. So an example of a problem that would look like this would be like, I don't know, natural log of 7, of 3x, right? And if I want to take the derivative of that, I would do the derivative of the inside, which is 3, over the natural log of 7 times the inside. So that would be my derivative. Make sense? All right, let's go ahead and practice. Let's do a few more. Let's look at example number 1. And I want to find the derivative of the natural log of 2x. Remember, anytime I do the derivative of a natural log, I do the derivative of the inside over the inside. So what is the derivative of the inside here? 2 over the inside, which is 2x. Can I go ahead and simplify this a little bit and say my final answer for my derivative is 1 over x? Let's do another one. I want to take the derivative of a natural log problem. I'm going to take the derivative of the inside, which is 2x, over the inside, which is x squared plus 1. Can't really factor that or reduce that anymore, so that would just be my final answer. That would be my derivative of that problem. All right, what about C? Look at C. C looks a little bit different. What do you think I have to do to find the derivative of x times natural log of x? Oh, isn't this a little product rule? I have a function here and I have another function here. I have two things being multiplied. So I can't just take the derivative of x and take the derivative of natural log of x and then smush them together. I have to use product rule. So let's go ahead and practice product rule. I have the second times the derivative of the first. What is the derivative of x? 1 plus the first times the derivative of the second. What is the derivative of natural log of x? It's the derivative of the inside over the inside, right? So 1 over x. Let's go ahead and simplify this a little bit more, and let's call it natural log of x plus 1. That would be my derivative of that problem. Let's look at D. D looks a little bit different too, doesn't it? Don't I have a natural log of x cubed? And be careful, it's not just an x cubed, so I can't just take this little 3 and bring it up front. The whole thing is cubed. So really, what rule am I doing here? Aren't I really doing chain rule here? Where this is my inside and I've got to bring up my exponent, keeping my inside the same, subtracting 1 from my exponent, and then don't forget to take the derivative of your inside. Well, the derivative of my inside is a natural log of x, so what's the derivative of my inside? 1 over x. Okay? So you could rewrite this 3 times the natural log of x squared all over x if you wanted to. Okay? Alright, so that would be my final answer on that one. Okay, so make sure you know your product rule and your chain rule still. It still does apply if the problem calls for it, okay? Alright, let's do a couple more. 2 last ones. These are going to get a little bit harder, a little bit more challenging, but we can do it. I'm still finding the derivative of a natural log, right? So I still need to take the derivative of the inside over the inside. But let's rewrite it first. Is there a way that I can rewrite this function a little bit differently? Can I do natural log of x plus 1 to the 1/2? Could I still write it differently? Right now, the only thing that's to the 1/2 power is that little x plus 1. Isn't that like a little expanding rule with a little x on it there? So can I take this and bring it down? Can I call this really a 1/2 natural log of x plus 1 using my expansion rules? Okay? And then can I take the derivative of this? I have a 1/2 out in front, which is just a number. It's just a constant, and I'm going to keep it out in front, and then all I have to do is worry about the derivative of my other stuff, right? So to take the derivative of a natural log, I do the derivative of the inside, which is what? 1 over the inside, which is x plus 1. So simplifying that, my final answer would be 1 over 2 times x plus 1. You could FOIL the bottom through if you wanted to, or you could leave it like that, either way. Okay. Last one, let's do B. Lots going on here. What do you think we can do before we even start taking derivatives? Let's go ahead and expand it. All right. So my f of x is really, let's see here, natural log of x. And instead of multiplying, I can add the natural log of x squared plus 1 squared. Ooh, can I bring that 2 up in front right now? I'm going to do that. I'm going to take this 2 and I'm going to bring it up in front.
Then I have dividing, but when I expand, dividing really turns into a subtraction. So then I have the natural log of 2x cubed minus 1 to the 1/2. And again, can I take this 1/2 and bring it up in front instead? So now that I've expanded, it's going to be a little bit easier to find my derivative, because now I can just find the derivative of each little piece instead of trying to do some weird quotient rule when I take the derivative if I were to try to take it from the very beginning. Okay? So now let's go ahead and find the derivative of each little piece. What is the derivative of natural log of x? 1 over x. I have a 2 out in front. I'm going to keep it out in front, and then I'm just going to find the derivative of the natural log of x squared plus 1, which is 2x over x squared plus 1, the derivative of the inside over the inside. Minus, I have a 1/2 out in front. I'm just going to leave it there, and then find the derivative of this other piece, which is what? 6x squared over 2x cubed minus 1. I can try to simplify this a little bit more. I have a 1 over x. I have a plus 4x over x squared plus 1. And I have a, can I take this and reduce it? Make that really a 3x squared over 2x cubed minus 1. None of those little pieces can be factored, and none of those are like terms. And so if I were to try to combine these guys, I would need a common denominator. It's going to get a little bit ugly, so you know what, I'm going to go ahead and stop there. If I'm just looking for derivatives, then isn't that still good? Now maybe later on, if I were to have to find my critical numbers and set this equal to 0 or doesn't exist, then maybe I would want to combine those before I can solve it. But if I'm just asked to find the derivative, let's go ahead and stop there. Okay? All right, so make sure you know your natural log values. Make sure you can find the derivative of a natural log by doing the derivative of the inside over the inside. Make sure you know your little log properties where you can expand certain problems. Make it a little bit easier to find the derivative, okay? We're going to go ahead and skip that last thing. Oops, there goes one back. And your homework for 5.1 is on page 330. I would like you to do numbers 45 through 59 odd and numbers 77 and 79. It is super important that you know how to do derivatives of natural logs because they do show up. They show up on your test, they show up on your final, and they show up on the AP test in May, okay? So go ahead and do 5.1 for me, and I'll see you tomorrow.